Okay. So, to make a new note. So, hope you guys liked your Friday off. I saw some people on there. I made a lab video, lab 1, in case you want to look it over on your own. Oh, big news. I'm a YouTube star. No, but I did make a channel. So I'm well on my way to being a YouTube star. Someone in my other class on Thursday said, well, you know, if you get enough views, then you can get paid. And I said, well, technically I'm already getting paid. So, okay, we've had this problem before. I know how to fix it this time, right? I just had to mute all. Okay, so I'm officially giving up on Slack. Congratulations to everyone who made it on there. It was just too hard to get everyone on, so I'll try again next term, I guess. So I've kind of migrated everything over to Moodle. Everything's there. And if you were on there this weekend, you saw that I posted a link just to my YouTube channel where I'll be posting all my lectures because I quickly ran out of Zoom storage. So I couldn't store them there anymore, so I had to think of another way. And so YouTube it is. So all my lecture videos, so my business math ones go on there too. I haven't split them up or anything. So all my videos are on that link there. So you might have to scroll through or kind of know what you're looking for, right? But they're all there. It is a little bit of a hassle to get them posted there. So you have to download them and post them and blah, blah. But I'll try to be as quick as I can about it. Okay. Cool. So I didn't do it today, but for later, I have to look into just having like a permanent Zoom meeting room open. So then if you do want to join in from home, that's great. You can just log in through Moodle and you shouldn't have to download anything or should just let you go and watch, okay? But like I said, the videos will be available and all that fun stuff. Oh, don't fall asleep. I'm talking to the iPad, not you. Any questions before we do a quick review? Cool. So you're all working on assignment 1. If you didn't get a printout, you do have to hand it in on the printout, right? So if you didn't get one and you haven't printed one off, you can grab one later. If you didn't get a formula sheet, you can grab a formula sheet as well. All right, make sure it's a nice-ish looking one. They've been used before, so who knows what they've been through. A final exam or two. Yeah, rough times. Okay. So, visit my YouTube channel. For lecture videos. You can just search Emily Lee. Even though I'm the only match, I think I'm the 3rd hit. I know, I've got some work to do there. But I do show up there, so that's all you need. Last time I checked, it said I only had 1 video, but then I had more, so that was good. All right, so assignment 1 is due next day, right? Beginning of class. I won't be accepting any late assignments. In fact, if you want to hand yours in early, that's real nice. Kind of skip the stress. Assignment number 1 is due Wednesday at 8 a.m. No late assignments will be accepted. Okay. You all have ways of getting assignments to me, even if it's not a physical copy, right? You can take pictures of it, scan it, send it to me, hand it in physically early. I don't care, just get it in on time. Otherwise, I will be a hard ass and say no. Okay. Mostly because assignments aren't worth that much, and well, I don't care. So let's do a quick review. Last day we finished chapter 1. Okay. We don't have time to do an example, but you're getting practice on the assignment, right? And I realized I forgot to post them, so I'll post them today. I have some chapter 1 practice problems with solutions. So just kind of problems that I put together and with solutions, so you can just work through those and have a look at the solutions. Are you on the right track? Are you not on the right track? Some of them are a little bit more involved than what I would expect from you, right? Especially on a test. But in general, they're just there for good practice problems and working backwards problems. You like to do that. I like to do that. So we finished chapter 1. Right, so we talked about the 5-number summary. We talked about, what else did we talk about? Finding outliers, right, using the 1.5 IQR rule. Finding outliers using the 1.5 IQR rule. And then we quickly finished with 1.7, where we talked about categorical data. Categorical data. We said we're not going to be too concerned about categorical data, especially later in the term, but we visualize using bar graphs. Or I'll put it in here because I use them interchangeably. Bar graphs, bar plots, pie charts, bar charts. Okay, they all mean the same thing. Because I had someone last term say, well, I didn't know what you meant because you called them bar graphs in class, and then the question asked for a bar chart. I said, okay, you got me. So now I've just outlined all of them, okay? Graphs, plots, charts, they're all the same, okay? So we should visualize using bar graphs or bars, right? Because they're the only way that we can detect the small differences, right? An industry favorite, although shouldn't be, is the pie chart, right? Or the new donut chart, with the hole in the middle. We shouldn't be using those, right? Just because it's hard to detect any small differences between your groups, okay? So remember, categorical data, you have your categories, and then each category has some count, right? So some number of your sample size is in there. So we should report categorical data, report as proportions instead of raw counts. Okay. So the proportion of people with brown hair, for example, the proportion of people with blonde hair, right? The proportion of people in first year, second year, third year, fourth year, right? So a proportion, remember we said, is the number in a category. So the raw count in a category over n, right? Where n is the sample size. I mentioned that very early on, right? But that's something that I expect you to know. So a lowercase n denotes the sample size. Okay. And very important, I have my favorite, oh man, okay, no matter. Come on. It's important, guys. Oh. I need to make it bigger. Oh. I'll get there. Can you see it? He's made a pie chart of his favorite bars and a bar chart of his favorite pies. So that's funny. Anyways. Worth it? I don't know. Okay. Does that even make sense? Not really. I don't know how you would get a count of your favorite bars unless I went around the room, right? But then it's our favorite bars and our favorite pies, right? That's how we would collect categorical data like this. So I would ask you, well, let's keep it PG. What's your favorite pie? What's your favorite pie? Your favorite pie? And then we get all our categories, right? And then we can make bar charts representing how many people like apple pie, cherry pie, blueberry pie, strawberry rhubarb. Right? Yeah.
What if you counted how many times in a year you have to eat your ghost bar?
That's another option. Yeah. Yeah, so I've been trying to figure out like ways that you could collect this data, but yeah, so one of them would be exactly how many times do you go to each of these bars, right? And then I guess you would see your favorite bar in case you didn't know, right? But I just think it's funny. Okay, so I'll just, because I have some room here. This is the end of chapter 1. You made it. Nice work. Okay. So now we're going to get into chapter 2. And there's been some development. I guess we have a sort of shared final with the Stat 124 crew, business stats. Hopefully you're not, alarmed because they're the exact same course essentially. So just be cool, okay? Everything's fine. I do have some kind of sway with you guys just being the 121s and they're the 124s, and so you guys are the only 121s this term, so that's good. But I do have to kind of stick to the norms. Usually I try to minimize the number or the amount of chapter 2 stuff because I don't like it. So then it rubs off on you guys and you guys end up not liking it. I'll try to make that not happen this term, but it just always happens. So it's on probability. More, we're going to be dealing with probability throughout the term, okay? But this is a very specific probability, and it's the kind that you probably think of when you say you're taking stats and you haven't actually taken it yet, right? So the probability of, drawing this card out of a deck of cards or something like that, rolling this for 5 rolls of dice or something like that, right? So it's a very particular kind of probability, but I just call it probability. So I'm short one day. So either I have 2 options. I can cut conditional probabilities or binomial probabilities, and I'm leaning towards binomials. But so today we're just going to start chapter 2, and then next day, stay tuned. We might be going into 2.2 or 3.4, but not both. Okay. I just have to check out the layout of the final again and see what's going on. I don't want to leave you guys stranded. So chapter 2. Oh, any questions before we get going into chapter 2? Probability. So first, let's just define probability, right? So the probability of an outcome is the proportion of times that a certain event would happen if we repeated this process an infinite number of times, right? So the reason that we know that flipping a coin, right, has a 50-50 chance of being heads or tails, right, is because, well, A, they have an equal, well, probability of having the outcome, right? And there's only 2, but also if we flipped a coin an infinite number of times, we would get a 50-50 distribution. Okay? And so probability, by definition, the probability of an outcome, is the proportion of times, the outcome would occur if we observed the random process an infinite number of times. An infinite number of times. Okay. So here's something to keep in mind. So a probability is the same as a proportion. Okay, so we can actually use those interchangeably, and a proportion is basically the same as a percentage, right? So 4 in 10 people say this, right? 40%. So 4 in 10 is 0.04, right? Or 0.4, sorry. So then, but we can convert it to a percentage by multiplying by 100. So we say that a proportion is almost or approximately equal to a percentage. Okay. So we need to get comfortable with all these 3 P's because they're essentially the same thing. Right? So probability is a proportion, which is essentially a percentage. Okay. And in our definition of a probability, right, we talk about a random process. A random process is just any process that yields some random outcome. Okay. So a random process, let's see, is any process that yields a random result. That yields a random result. Okay. So for example, a random process would be if you flip a coin, right, then we can denote the random results. We either get heads or tails. Right. If we roll a die, right, then the result is random and we have 6 possible outcomes, right? 1, 2, 3, 4, 5, 6. Okay. So roll a die is also a random process, and the random result that we could get from it is 1, 2, 3, 4, 5, 6. Okay. So what we're noticing here, right, is that each random process has a finite set of outcomes, right, possible outcomes. We call that our sample space, right? So this is where all our outcomes could come from. There are no other outcomes. Okay. So each random process has a set of possible outcomes. Possible outcomes called the sample space. Okay. The sample space is denoted by, a capital S. So when we're talking probability, right, and we say, okay, the probability of rolling a 1 when we roll a die is this, right? That's a lot of words that we don't really want to be writing down, right? So to make our life easier, we use probability notation. Okay. So we use probability notation and just in general, it's going to look like this. It's going to be a capital P and then bracket, and then A is the random process, right, or the random outcome, depending on what you're talking about actually, and then end bracket. So you're going to read this as the probability of A. And we said this in the lab too, right? We're going to have, we looked at the summary command briefly, right? So it said summary and then brackets and then summary of whatever was inside the brackets, right? So whenever you see the brackets, you're going to read P of A, right? Summary of A, mean of A, right? And so that's how we're going to get more comfortable with this notation. Okay, I'm not sure if you've seen probability notation before, but I'm going to say no. If you have, that's great. Okay.
It represents the random process, correct?
Yeah, or the random results, depending on the scenario. So if we know the context, so here, yeah, good segue. So if we know the context, right, then we can use shorthand notation in our probability notation. So if we know the context, which we will, if we know the context, we can specify an outcome, right? And we can say stuff like P of H, right? Just looking at our list here, or even if you had to guess, probably you would say, oh, I'm flipping a coin and probability of a head, right? So the probability of getting heads when you flip a coin, we say is 0.5, right? So all these probabilities are going to have values attached, right? Because we know there's a 50-50 chance. Of course, the probability of tails is the same. Or if I say that I'm rolling a die and the probability of a 2, for example, is 1 in 6. All right. I keep it as a fraction if it's convenient, right? This one would have a bunch of repeats, so I just keep it as a fraction, right? But if it's a nice decimal, then go ahead and use it. Right? But you don't want to be rounding, right? 1 in 6. So it means we have to know the context. In this course, we'll always know the context of the probability that we're talking about, right? So then, so if I say you're rolling a die and what's the probability of 3, right? Say 1 in 6. Right? Often it's the other way around. I tell you the probabilities, right? Because I'm not expecting you to know how to calculate probabilities quite yet, right? I tell you each of the probabilities, and then you need to know how to work with them. Right? So when we're talking probabilities, there are some key facts that we have to keep in mind. Okay, so some probability facts. The first one is that a probability has to be between 0 and 1. You can't have negative probabilities, and thinking in terms of percentages, right, because that's usually where we go to, we can't have a probability higher than 100%. That just doesn't happen. Right? So a probability must be between 0 and 1. Otherwise, it's not a probability. And then our second fact is that the total probability in your sample space, remember the sample space is a list of all the possible outcomes. Right? If you're adding up all the probabilities associated with each of the possible outcomes, they have to add to 1, right? If they don't add to 1, you don't have all the possible outcomes, right? So, bless you. The total probability in your sample space must add to 1. So I give you these on your formula sheet, okay? And it's the first 2 lines in your chapter 2 probability section, but they're denoted a little bit differently. Okay? And so these facts are given on your formula sheet as the first one, it says that P of A, so any outcome A, has to be between 0 and 1. And the probability of S, remember S denotes the sample space, has to be 1. So those two facts are on your formula sheet, and you have to know how to use them. Okay? And we'll come to that in just a little bit. So this probably isn't the kind of math you're used to, right? But stats and math later on is just a bunch of definitions, and then it's your job to know how to apply them, right? And so it is going to feel like I am hitting you with just definition, 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 but notice that as I'm introducing them, I'm expecting you to know them, right? So now I'm talking just freely about the sample space, and that's why it's important that you go home and review these. I know that these probably aren't sticking right away, right? But I do expect you to know them. Once I've defined something, right, then I expect you to know that. Okay. So, more definitions. So, two events are considered disjoint, right, if they can never happen together, right? The probability of them happening together is 0 because they can just never happen together, right? I can't flip a coin once and get a head and a tail, right? So there's no probability of them happening together, right? And so two events are disjoint, or you know what, I'll say events or outcomes. I get a little lazy defining these. I kind of use them interchangeably. So just beware. So two events or outcomes are disjoint or you might have heard the term mutually exclusive, right? We use that sometimes. Or mutually exclusive. If they cannot both happen at the same time. They cannot both happen at the same time. Yeah, so for example, squeeze together. Oh, all right. Flip a coin once. Oops. We only get a head or tail, never both. Just as a counterexample, which we'll get to a little bit later, is if you're considering a deck of cards, right? And I ask you, so here's two outcomes, either drawing a face card, right, or drawing a red card, right? There are red face cards, so those two things are not disjoint, right? Red card, black card, those are disjoint, right? You can never pull one card and get a red and a black card. It's one or the other. And so if they can happen at the same time, then they're not disjoint. So, like I said here, right, I interchange events or outcomes. Events are a set of outcomes. Okay, so events are sets of outcomes. Okay. Or I guess collections of outcomes. So for example, say I don't care if I roll a 4 or a 6, right? But I'm looking for the event a 4 or a 6, right? Then I can list this event, right? So let's just write it out here. So say I'm interested in the event rolling a 4 or a 6. We can call this event something. Usually we use capital letters. So we can call this event something. Let's call it capital B. Just completely arbitrary. So then we would say that B is the event, and I'm using set notation here, curly brackets, okay, of a 4 or a 6. So 4 comma 6. Curly brackets are just set notation. It's not something that I'm gonna test you on, right? Just kind of be okay to read it, right? And so each of these outcomes, right? If you roll a die, the outcomes 1, 2, 3, 4, 5, 6, right? Those are individual outcomes. Technically, each of them are an event as well, right? Or an event can have more than one outcome in it, right? Like a 4 or a 6. I don't care about either of those. So then we can still talk about the probability of B, right? Which is the same as the probability of a 4 or a 6. And because, and only because 4 and 6 are disjoint, right? I can't roll a die and have a 4 and a 6, right? I get either a 4 or a 6, so they're disjoint. Then because they're disjoint, we can reduce this to the probability of 4 plus the probability of 6. But this is because 4 and 6 are disjoint.
What if they weren't?
Then we'll get to that in 2 or so pages. Okay. Right, because we know that there's a lot of outcomes. In fact, the things we're interested in are usually not disjoint, right? Like counting cards. That's what we're here for, right? So the probability of 4 we know is 1 in 6, and the probability of 6 is 1 in 6. So I'm just going to leave it as 2 in 6. But not something that I'm expecting you to derive quite yet. Okay. So we know that this is a special case, right? When 4 and 6 are disjoint. So, or any two events that are disjoint. Okay. So let's talk about what happens when these things are not disjoint, right? So, I'll say events or outcomes that are not disjoint. So kind of a famous example, right, and I've already used it, is our deck of cards here. So I'll just sneak it in. Just so we have it. So each of the suits, right, are disjoint from each other, right? I can talk about hearts and diamonds. If I'm just pulling one card, then those two things will never happen together, right? Red and black, same thing, right? But then we have these kind of, well, the easiest to see probably is the face cards, right? And each of the colored face cards. So if I'm talking about the event of drawing a red card and the event of drawing a face card, right, those two things can happen together. So we need to know how to deal with that because it affects the probability, right? So if we're talking about just the probability of, oops. I'll just say in a deck of 52 cards, oops. And no, I'm not expecting you to know what a deck of cards looks like, but a general idea helps, right? And so each of the suits has 13 cards, 3 of which are face cards, right? And there's a total of 52 cards. And so, and 26 of each color. We can say something like the probability of F, you can probably guess that F is a face card. Right? We can just count how many face cards we have, right? And it's going to be 12, right? 3 for each suit, 3 times 4. So the probability of a face card, we say, is 12 out of 52 cards. Right? Yeah. What if I asked you, just looking at this little graph here, what's the probability of a diamond? Okay. So regardless of what number it is, right? Perfect. So the probability of a diamond is 13 out of 52, right? Because we're just looking here and we're saying, okay, so for our probability of a face card, we're saying, well, we have 12 face cards out of 52. So the probability of a face card is 12 out of 52. Right? And then we do the same thing. I ask you, okay, look at the diamond. So now you're just looking at this row. And the probability of a diamond then is 13 out of 52. But if I asked you, what's the probability of a diamond or a face card? Right. So now it doesn't matter which one. So if you have a diamond or if you have a face card, you count them up in your little tally, right? And so we have 1, 2, 3, 13 we decided, right? But then we've already counted these 3. So 13, blah, 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 right? So we're going to work into it. So how do we find the probability of F or D? Right. We can't just add up the probabilities because we see that we have the overlap, right? The diamond face cards. We can't simply add our probabilities, which is what we did in the disjoint case, right? So we can't just add our probabilities because we have 3 cards of overlap. Right, the diamond face cards. So what we would do then, right, is we would say, okay, well, the probability of F or D, we can start with and say, okay, well, we're going to look at all the face cards, right? It's the probability of F plus the probability of D. We can do that, but just recognizing that we have that little bit of overlap, right? And that overlap is where we have diamonds and face cards. Right? And so we have to subtract the probability of F and D. Or in general, so this is our general addition rule. It's the one on your formula sheet. Or in general, we have the probability of A or B. We're going to find the probability of A plus the probability of B, whatever they are, minus the probability of A and B. Notice that the disjoint case is just a special case of this, right? Because if A and B are disjoint, right, by definition, the probability that they'll happen at the same time is 0, right? And the probability of A and B would be 0 then, right? So then you just have probability of A plus the probability of B, right? So if A and B are disjoint, the probability of A and B is 0. So we start with the disjoint, right? Because that's kind of where we start in our minds. Right? We just say, oh, this plus this, right? And then we say, well, that's only true for if A and B are disjoint, right? And so that's why you only have this general addition rule is what it's called. I'll just put it here. It's called the general addition rule. So you only have this on your formula sheet, right? Because if you figure out that A and B are disjoint, right, then you know that the probability of A and B is 0. And so you can just plug that in, 0, and it goes away. Cool. Any questions so far? Okay. So here, let's just say, right, we have 1, 2, 3, 4 pieces of information. Right? And so what I'm expecting of you is if I give you 3 out of these 4 pieces, I can ask you to solve for any one of the missing pieces. Right? So given 3 of the 4 pieces, let's say, we can solve for the 4th. Let's see if I had an example here. Not quite yet. Okay. Sorry, no examples yet. Okay. So I could give you the probability of A or B, the probability of A, the probability of B, or the probability of A and B, and ask you to solve for one of the missing 4. Okay. So, I know this is a lot, but it'll be fine once we see examples. When are they coming? Just hang tight a little bit longer. So let's talk probability distributions. So probability distributions is really just a table of the set of all possible outcomes, right? So we just list all our outcomes and the probabilities of each outcome below it. So nothing too crazy, but probability distributions are a table of all possible disjoint outcomes, meaning, so all possible outcomes, that has to be the sample space, right? The sample space with, oops, I always do that. I try to combine with the as just one word, just becomes wide. With the probability of each outcome listed below it. Outcome listed below it. Okay. So this should sound familiar if I tell you that a probability distribution is only valid if, well, the first one is kind of new, if each of the outcomes are disjoint. Right? Second, if all the probabilities are between 0 and 1. Right? And if the sum of all the probabilities is 1. Right? That makes it a valid probability distribution. A valid probability distribution. One. All outcomes listed are disjoint. Right? We can't have any overlap in our list of possible outcomes. 2, I'll use the notation on your formula sheet, right? Each probability has to be between 0 and 1. Or I'll put it in brackets here. Each probability must be between 0 and 1. And finally, the probability of the sample space has to be 1. Right? So the sum of all probabilities must be 1. So I'm going to steal a little example from here. Oh, it's a little random Venn diagram. So here's a probability distribution, just for rolling 2 dice. I always get them mixed up, but you can only die once. And so that's singular. Dice is plural. Here we go. So you're rolling 2 dice, right? And so we're talking about the sum of these 2, right? That's more interesting than just rolling 1 die and being done with it, right? And so here we have a list of all the possible outcomes, right? We're only talking 6-sided die here. And so our lowest total possible is 2, right? 2 1s. And our highest possible total is 12, 2 6s. Right? And then everything in between. And so then, so here's a list of all our possible outcomes, right, between 2 and 12. And then each probability, right, notice that it's going to change. Why? Because there's only one way that you can get a total of 2, right? A 1 and a 1. But there's 2 ways to get a total of 3, right? 1 and a 2, 2 and a 1, right? Those are 2 different things, right? And 3 different ways that we can get 4, right? 1 and a 3, 3 and a 1, 2 and 2, 2 and a 2. Oh no, 3. That's good. Right? And so we're increasing until we hit a peak at 7, right? So just looking at this probability distribution, you know that rolling a total of 7 has the highest probability, right? And so it probably pays the least if that's what you're betting on, right? Whereas if you're betting out here in the flanks, right, you'll get better payouts because the probability is smaller. And so that's how these things are set up. And so this is a valid probability distribution, right? And we can check. So in a question, I would say, is this a valid probability distribution? First thing you're going to check is, well, each of these outcomes, they are. That's so sweet. So I thought it was yesterday, but I guess it's today. What was I saying? Yeah, each of these outcomes, they're disjoint, right? And each of these probabilities, we can just kind of visually check them, make sure that they're all between 0 and 1, which they are, right? And if we added up all these, we would get a total of 36 over 36. Right? So if I ask you, is this a valid probability distribution? Then those are the three things that you would go through and check. Right? So I think I have another example. It's flawed, but I stole it from a textbook, so it can't be that bad. Oh. Come on. Why won't it? There. All right, whatever. Quick example. So the table below suggests 3 distributions for household income in the United States. Only one is correct. Which one must it be? What's wrong with the other 2? Okay. So basically, I'm asking you find the valid probability distribution. So I give you a list of probability distributions, and I'm asking you which one of these is valid. Okay. First thing we check, and here's the flaw, right? Are these disjoint? Right? Are each of these categories disjoint? If we're just looking at it, no, right? Because we have 0 to 25 and then 25 to 50. So 25's in there twice. But what I'm going to say is we're going to assume, right, that this is actually, it's household income, right? So let's say 24,999, right? And then here we have 25,000 per year, right? And so we're just going to assume that they're disjoint, even though it looks like they're not. Right? So I'll just make a note here. Assume the outcomes are disjoint, even though it looks like they're maybe not, but they are, I promise. So that's the first thing that we check, right? And then the second thing that we check, right, is all the probabilities have to be between 0 and 1, right? And so we see this negative probability, so B is out immediately, right? Because we can't have a negative probability. Right? So B is not valid because we can't have a negative probability. So now the rest of these 2 look fine. So I'm going to add another column here where I have the sum. So I'm going to add these up, just go across the row, because what's our third condition? Right, it's that the total probability has to be 1. Right? And so if we put the sum on here, we get 0.18 plus 0.39 plus 0.33 plus 0.16. Uh-oh, trouble in paradise. 1.06. Okay. So B isn't a valid probability distribution either. Okay. Sorry, A. I already talked about B. A is not valid because the total probability is not 1. So let's just check the C probability 0.28 plus 0.27 plus 0.29 plus 0.16. Phew. Who would have guessed that it was the last one? Okay. So C is a valid probability distribution as all probabilities, probs, are between 0 and 1, and the total probability is 1. This says the So I'll give you something like that on the test, right, where I give you a list of probability distributions, and then I ask you which one is valid. Right? And you just have to remember to go through and check those things, right? Are they disjoint? All the probabilities between 0 and 1, that's on your formula sheet, right? And the sum of the probabilities has to be 1, also on your formula sheet. Okay. Any questions about that? No? It's all a blur. That's okay. So now we're going to talk about the complement of an event. The complement of an event is when it doesn't happen, right? So we can refer to events as kind of the opposite, right? So rolling a die and I roll a 2, or another event, right, is not rolling a 2. That's rolling a 1, a 3, a 4, 5, or a 6, right? So we can talk about events as the complement of another event. Okay. So the complement of an event is all the outcomes when the event doesn't happen, is all the outcomes when the event doesn't happen. And so it's denoted as A and then superscript C or A complement, A not. Okay. And I read these as A not, right? Or not A. You could say the complement of A. But in my mind, it makes more sense to just talk about, okay, well, the complement of A is just not A. Right? So everything in not A. For example, if B, just some random B, is that list of outcomes 4 and 6, then the complement of B is going to be 1, 2, 3, not 4, right? Because 4 is in B. 5, and then not 6 because 6 is in B. if you have a peek at your formula sheet, right, you could have probably guessed it, right? But if I say that the probability of, I don't know, of a plane crashing is 0.2%, or let's do just 2%. Oh, large. Ugh. Should have picked a more pleasant probability. Anyways, right? And I asked you, what's the probability of the plane not crashing? Y'all would say 98%, right? If I told you that the probability of it crashing is 2%, the probability of it not crashing, right? We all kind of intuitively know that it has to be 98%, right? And so in probability notation, okay, so in general, the probability of the complement of A or not A, right? So now we're talking probabilities, right? Not just the list of outcomes. So the probability of the complement of A is just 1 minus the probability that A actually happens, right? And vice versa. The probability of A is 1 minus the probability that A doesn't happen, right? And that's on your formula sheet. But I think we all just kind of know it, right? For example, if the probability of getting an A on the test is 60%, what is the probability of not getting an A? Convenient notation, talking about A's with just A's. Then the probability of the complement of A is just 1 minus 0.6, right? 60%. That's the probability of getting an A. But you already knew this answer, right? Without the notation. You would say 40%.
But obviously we would have to show our work.
Yeah. If you're in the test and you hit a jam, what I want you to do is I don't want you to get hung up on the probability notation, because I know it's new and foreign. If you write it out, right, and explain to me exactly what's going on, that's the same thing, right? It would just take a lot more words, right, than just using probability notation, right? You would just have to say that the probability of the complement of A is 1 minus the probability of A, right? A being getting an A on this test. Right? And so you'd have to use all your words properly, right? But as long as you say what you need to say, right? You don't have to use probability notation, but I think you'll find it much easier. And I'll be using probability notation because I don't want to write all this stuff out. Okay. So, let's quickly talk about two independent events, right? So we've talked about disjoint events where the outcomes have no outcomes in common, right? Or the events have no outcomes in common. Those are disjoint. But independent events are a little bit different because independence has to do with the probabilities, right? Not the outcomes themselves. So independent events are when outcome of one doesn't affect the probability of another, right? So a lot of things are not independent, right? And so let's talk about when are they independent and when are they not. So two events are independent if knowing the outcome of one does not affect, oops, oh man, does not affect the probability of the other. Okay. Some examples, right? If I flip a coin, even if we want to think that, oh, we've seen 5 heads in a row here, this next one has to be a tail, right? That's not how it works. These are all independent events. So even though we want to think that, oh no, there's been so many heads now that we're destined for a tail, right? That's not how it works. These are all independent events. Same with rolling a die. Even if we see a lot in a row, right, that's highly unlikely, right? But they're all independent events. Things that are dependent, right, so not independent, things like disease, right? If you were exposed to the disease, you're more likely to have it, right? Stocks, right? One goes up, all the others kind of go up with it, right? One falls, they all just kind of, right? They follow each other, right? Weather, we're not expecting to see snow tomorrow, knock on wood, right? Because we know that there's going to be this kind of steady trend, right? Kind of continuous change. Okay, so we'll just leave with some examples here. So independent examples. Things like flipping a coin or rolling a die. Dependent events, things like stocks or the weather, disease, things like that are not independent. I don't actually call them dependent that often. I just say they're not independent, but that's okay. Hopefully you know what I mean. Okay. So I think we'll leave it there for now. I'll see you on Wednesday. Woo.